Okay, so welcome to the study session for the first test in Physics 202. Any questions? Yes?
Number 2 on the study guide, you couldn't figure out the magnitude of the electric field at points.
Number 2 on the study test.
Yes.
Anybody else have that problem? Okay, magnitude of direction of the electric field. We have 2-point charges. And we're looking at a point in space. All right, so hopefully I don't have a typo on this. Did anyone else get the answer? Did anyone get the answer?
Yeah.
Yeah? Okay. So first of all, we're looking at a point in space. So we're going to look at the magnitude due to each source separately. Okay. So let's call this the charge 1 and this 2. The E due to charge 1 is equal to, what's the equation for the magnetic or electric field?
KQ over R squared.
KQ1 over R1 squared. So that's going to equal 9 times 10 to the 9th times 2 times 10 to the minus 6 coulombs divided by 0.2 squared. Okay. In what direction will that point? Okay, so what's our test for the direction of the electric field? Away from positive charge towards negative charge, or if you don't know, put a positive charge there and the force will tell you where it goes. Okay, so at this location, this electric field points to the right. And so let's call this a positive number. Any idea what that is?
450,000.
450,000. Okay. Then we have, we do the same exact thing with this being the source charge. And in this case, what's the number? 270?
Is the negative 12 an absolute value or no?
The equation is absolute values, yes.
Okay.
27 with 5 zeros.
2750?
Well, there's 5 zeros on the end.
There's 5 zeros on the end.
There's no 5. Is that 5?
No, 27 with 5 zeros.
Oh, that's what I meant,
Okay. In what direction does that point? This equation gives us the magnitude, no direction. What direction does that field point? To the left or to the right?
To the right.
To the right, towards the negative charge. This is a negative charge. So it is also okay. And then you just, now that they're pointing in the same line, we can add them up mathematically. So those add up to positive 43150,000 newtons per coulomb. So is that right?
Yes.
Okay.
So R2E is 0.4 or no?
R2, what's the value of R2? The distance from this charge to this location. It's also 0.2 meters. Okay? So we had 0.4 minus 0.2 leaves 0.2 meters. Okay? Question? Yes.
For 2C, can it be negative or should it be negative? Because,
The electric potential energy?
yeah,
Oh,
it uses a negative charge.
that might be. I believe it should. And what's the equation for electric potential energy? KQQ over R. And in this case, it's not absolute value. So excellent point. Did anyone else notice that?
It's negative?
Because it's not absolute value and it's a negative charge. Yeah.
So the question was, on the next question, we say, what's the magnitude, or what's the size of, in the previous question, rather, we say, what's the electric potential energy between the two charges? And they have the ability to fall into each other. So that's attractive.
I was going to say, yeah, negative force. Or, I mean, yeah, negative. And
So that would be a negative number. I think that's correct. Does that make sense, that it's negative? Okay, so let me...
Besides the fact that the charge is
But what we're saying in the previous question, which is the third one, I guess if you call it ABC, the electric potential energy between these two charges. And in this case, we don't care about this point in space. We're just looking at these two charges. So U equals K Q1 Q2 over R squared.
Over R.
R, sorry, R. Just R. Okay. And so that's a constant times a plus times a negative divided by R. What?
divided by R.
I'm okay. You were just, that's great.
Hopefully you're laughing tomorrow.
I will.
Okay.
By laughing, he's crying. Yes.
Does this look like the video is visible at all? Is it kind of coming through?
I mean, it looks like
And it
it.
says like record on the top.
Oh, yeah, it's recording.
Excellent job.
It just looks tiny.
All right. Any other questions on this one for problem number 2 on the sample test? Yes.
Wait, R would be what again? From the point charge, is 0.2?
R would be the distance between the two charges. In this case, there's 2 questions here between the two charges, the force and the potential energy. And then there's then there are other questions about this point in space due to these two charges. So the electric potential energy is specific between two charges, and they're at a distance of 0.4 meters, so R should equal 0.4. Here.
Okay, so the R is the distance between the two charges. How about there was like more than like just 2 charges? Or like,
That's in the next problem. You do like from one charge to the X, and then the other charge to the X. Like you use.
Usually with potential energy, it gets really complicated really fast, so we try and keep it.
so it just sticks to that
Yeah.
base.
But yeah, be very careful what the R means in each problem. Yes, 2.
And then just add on to this, just so I don't get confused, just the scalar quantities and the vector quantities, only so far the equations we have.
We're on film here, and they won't be able to hear. They'll hear you more than the person. So, scalars and vectors, yeah.
Force is a vector, like electrostatic force, and the electric field is a vector. Like those two are the only vectors, and then electric potential energy is not a vector. Those are scalar quantities.
Correct, yeah. So, force and electric field are vectors. We have to keep track of where they point. And then electric potential energy and electric potential are both scalars. We just add them, the plus and minus signs count, but we just add them up. Chris, did you have a question?
Yeah, and it was electric potential, and what was the other one?
Electric potential energy.
Okay, does the paper of equations that were given for the test tell if they are scalars or vectors, or do we have to memorize that?
So the question is, will the handout This is the handout, this is the slide from chapter 21 slides. And these are bold, meaning they're vectors.
Okay,
These are
so,
not bold, meaning they're scalars.
so then we get that paper.
You'll get something like this plus a few other equations. If there's any equations or constants you need, just ask during the test.
Okay.
Any other questions related to problem 2?
You just mentioned the both charges zero, because that could be a positive charge, electric charge.
Okay, the last question is, where is the electric field due to both charges equal to 0? Not exactly, but generally. Okay? So in this situation, we want to break it into regions. This is a qualitative question, not a quantitative question. And so there's 3 regions here. There's this region over here, there's this region here, and this region here. What we need to do is analyze, in order to have the electric field equal to 0, we have to have one going one way and one going the other way. Does that make sense? So that there's a tug of war with the vectors and they cancel. So in the middle here, we had E1 pointing to the right and E2 pointing to the right as well. So they both go that way. So there's no way that in between here in this region, there's no way that the electric field can be 0. Because the 2 fields from each add up and point in the same direction. Over here, you've got a situation where what? If we're here, the electric field due to this charge points what way? Still to the right. And the electric field here points what way?
To the left.
To the left. Okay? So there's the potential to cancel. Are you saying the problem was answered wrong on the sheet?
I couldn't figure it.
Okay. Okay, so this looks like it could be a region where these 2, if we got the position right, could potentially cancel. Do we think they actually could cancel them?
No.
Why not? They cannot cancel because what?
They both have the same distance apart and the charges are not the same.
Okay, so this charge has a bigger magnitude than this, so it has more influence, and it's closer, so it has a lot more influence over this point in space than that. Okay? So E2 here is much greater than E1. E2 is much greater than E1 because it's a larger charge at a closer distance. So this charge has more influence in space than this charge. Therefore, you have a situation where they can't cancel. This way is going to be bigger. Does that make sense? Maybe sort of? Are we having filming problems?
No, I was just saying.
All right, what about over here? At this point in space, which way does E1 point?
To the right. No, wait, to the left.
To the left. So it would push a positive charge away. So E1 is this way. Which way does E2 point?
To the right.
To the right. Which one's bigger?
E1.
You don't know, and it's hard to tell. This one has a smaller charge, but it's closer. This one has a bigger charge, so it's farther away. There's the potential that at some location, and mercifully we don't ask you exactly where, but at some location, those 2 vectors would be equal and opposite, and they would cancel out. Does that kind of make sense?
Yes.
So that's actually a very difficult question to figure out during a test. Because you have 2 potential right answers. This and this both have vectors opposing each other. That's a pretty subtle thing to ask on a test. I'd be really angry at any professor who wrote this question.
So does this mean that you're not going to write one like that?
No, I'd have a lot of respect for that professor.
Okay.
Any other questions on 2? Okay, so you will see a problem almost exactly like this.
So not one like the kangaroo.
No. Not one like the kangaroo.
Wasn't the kangaroo one last semester?
It was last semester. Taylor?
So for part F, where it's asking you the electric potential at point X, is it the same as what we just did where you take each charge and then add them up?
It's the same procedure with a different equation. That's the same basic idea. Yep.
So just because that charge on the right is bigger, has bigger magnitude, that's why you can assume that the smaller one on the left side is going to cancel.
Okay, what I'm saying is this charge is bigger than that charge. So this one always has, and it's closer, so this one always has more influence over this point in space. So this vector is always going to be bigger than this vector.
On that side.
On this, in this region over here.
Yes.
But in this region over here, this is bigger, but this is closer. At some point, those influences could balance out. All right, excellent work. Can you turn the record off? What we're going to do is break this up into a lot of